Imagine for a moment the daily change of a painter cleaning letters, inhaling toxic fumes, and struggling to maintain a uniform finish on every wall. This happens daily in Lima, where construction is booming and interior painting is essential. Today, we present our project, design and implementation of a low-cost based teleoperated mobile robot with an adjustable lift system to autonomous paint spraying on interior walls at ROS-Gazebo, aimed at reducing occupational hazards and costs in Peruvian construction sector. This slide presents the index of the context of the partial presentation. Metropolitan Lima is the most dynamically growing city in Peru. The figures show urban densification, human settlements, and popular concentration. According to Capeco, in 2020, there were 4.9 million square meters under construction, although the sector contracted by 17% during pandemic. It grew in 2.97% in 2022. Inefficient manual painting processing construction involves high occupational risk, material waste, and poor quality, generating delays and higher cost. 50% of the amount is for painting budget and is used for cover unforeseen events and errors. 30% of the paint is wasted due to mistakes, and also the people who work with painting then have different affections on their health related with the breath and also with the skin, and this is because they are exposed to bugs. We found our engineering problem and what remote control and virtual simulation consideration in ROS-Gazebo should be applied in the design and implementation of a low-cost mobile robot with adjustment lifting system, which allows for uniform painting of interior walls and construction sites in Metropolitan Lima, reducing operator exposures to chemical and physical risks, and optimization the process time and costs. Miss Markevit is a commercial painting robot that has high costs, over than $85,000, and Okibo is a semi-autonomous vertical painting robot with fixed rails. Pictobot similarly uses a robotic arm mounted on a rigid structure, and our goal is to design an affordable alternative. Also, we have different publications. This publication is related with using LiDAR and an RGB camera. This publication is related with using Gazebo, that is a free software. That's why we also will use this software to do the implementation of this in 3D modeling software. How we will paint and is with airbrush nozzles. So it's about the pressure of the air in a spray gun.
Justification. Why is our robot the ideal solution? 3 key pillars. Safety. Eliminates faults and complies with ISO 10218. Efficiency. 40% faster and save 15,000 soles per project. Innovation. First Peruvian robot with ROS-Gazebo patent pending. Cost comparison. Our robot costs $10,000 to $25,000, 75 to 85% cheaper and made in Peru, versus Okibo from USA, Israel, or Pictobot from Singapore. Supported by Jimmy Day or Research Center, the Impulso Incubation Program, and funding from Unifin. Expert guidance from Master's Degree Engineer Ricardo Rodriguez Bustinza.
Our general objective is to design and implement a low-cost web-based teleoperated mobile robot with an adjustable lift system for spraying paint in interior walls, and this robot is validated in ROS-Gazebo and is aimed at reducing occupational hazard and costs in the construction sector of Metropolitan Lima. Our specific objectives are 3. We can see here. So we have the description. We can see how it's growing up. It's growing up the parts that will paint. We can see a wall, and also the painting could go until the up of the wall. This robot can go to 3 meters. And the software also, we see here that we have a graphic interface and also a 3D modeling of the robot. So there is a Here is a pictorial block diagram, and we can see the LiDAR, IMU, and camera, and the units of control, the motors, the system elevation, the spray gun, and also the part of alimentation and the chassis. So our methodology, this research is quantitative. Why? Because it's objective, deductive, verifiable, and result-oriented. The scope of this research is exploratory experimental. The theoretical framework is about the spray painting, more theoretical about the painting process, and about the occupational risk and cost operation. Also about what is ROS and what is Gazebo with ROS. Here are our potential users.
Technical feasibility. 3 key points guarantee our success. Our multidisciplinary team combines expertise in mechanical design, electronics, and software rules for SLAM. We are supported by engineer Ricardo Rodriguez Bustinza, a specialist in control and automation with more 20 years experience and full access to GMA laboratories resource, including LiDAR, Raspberry Pi, and motors. Economics and social viability. With a total investment of 35,000 soles for the development of the prototype, funding comes from Unifin competition covering 57%, GMA contributes 23% in equipment, and 20% comes from our own capital. The expected returns on investment in just 14 months. In addition, transformative social benefits align with the UN SDGs 3, 8, 9, and 12. This is a schedule. Budget breakdown, mechanical components, and electronics. Labor and certifications, logistics. Bottom line, 35,000 soles projected, 20,000 soles real cost. Our final project deliverables will include fully functional web-based teleoperation system, adjustable lifting mechanism for wall painting, ROS-Gazebo integration for autonomous navigation, low-cost Peruvian MADE prototype. Due to import delays, standard wheel instead of mechanism wheels, and the regular camera replacing inter-rail sense. Our academic plan will cover all key stages with the exception of testing in real-world construction environment. This final phase will be implemented in August 2025.
Also, we have image figures about how this will up and down. So we have the Lugri model that is used for the part that will be for the elevator system, for do the control of the elevator system. This is about the spray, how the spray will be different according to the pressure that we are using. So it's more about the mapping and the simulation of this lamp.
Here, the video shows the robot in the gazebo simulation, moving differentially. We can also see the upward and downward movement of the telescopic arm. In addition, the graphical interface for controlling the robot is shown. This includes button for controlling movement, slide for the arms, a section for sensor data, an area for the map generated by the LiDAR, and an area for the camera feed. Conclusion and final comments. Our solutions delivers 100 square meters of coverage per workday, 96% accuracy in paint application, zero exposure to foul or toxic fumes, while traditional methods mean 3 times slower productivity, high error rates, constant health risks. And finally, the bibliography. Thanks for watching.